Hi, my name is Javes Martinez, and with my group, Darlene Carrasquillo and Nicole Diaz, we're gonna present the Phase A of the Green Powered Medical Ventilator. Here we have the technology assessment at system level. These are the reference of different books that they will help us to solve the problems we could come with. Now, I'm gonna leave you with my partner Darlene.
Greetings. My name is Darlene Carrasquillo and I am going to talk about trace studies concept of variation. In first concept of variation, in step 1, connect the pressurized gas source, set inspiratory flow as just as needed. In step 2, set PIP with T-dial, verify operation with manometer and connect to patient. In step 3, as jet exhalation with rate dial, readjusts flow PIP rate as needed. As operational objective, install a system who provides continuous ventilatory support for 30 days and operates independently. Operates with electricity via simple connection to gas source. It will be reduce power consumption of the hospital by 100%. It will be use positive pressure ventilation that pushes the air into the lungs. Second concept operation. In step 1, initiation of an inhalation which is triggered by an effort from the patient or by set parameters by the mechanical ventilator. In step 2, inhalation of air into the patient. And step 3, passive exhalation of air from the patient. As operational objective, use a mechanical ventilation machine that takes over the work of breathing when a person is not able to breathe enough on their own. It will be require electricity power of 120 volts. In terms of concept of operation, in step 1, a medical procedure in which healthcare professionals will create an opening in their patient's neck to place a tube into their patient's windpipe. And step 2 allows air, allows air to enter the lungs. As operational objective, use an opening created at the front of the neck so tube can be inserted into the trachea by help you breathe. If necessary, the tube can be connected to an oxygen supply and breathing machine called a ventilator. Now, trace studies POC matrix. The problem statement of this POC matrix is design a low-cost jet-efficient mechanical ventilator for use in localities where modern condition of a steady, reliable electric grid is not available. The criteria for grid POC matrix are work without electricity power, lifespan, compact, and flexible weight. The weighting of these are 35, 20, 25, and 20. The baseline of datum are 0%, 419 cubic inches, and 117 grams. Concept of operational number 1, complete with all criteria and the total is 100. Concept of operation number 2, complete with use 1 criteria which is lifespan and has total of 20. And concept of operation number 3, complete with 2 criteria which are compact and flexible weight has total 45. Now we will continue with my partner Nicole Diaz.
Hi, my name is Nicole Diaz, and I will be presenting the project mission architecture and interfaces. The hierarchy diagram. The first thing is the limitations and energy consumption of mechanical ventilators. The system is power ventilator, and we divide the complete ventilator system into 3 subsystems. We divide the complete fan system into 3 subsystems that are run by Darlene, Javes, and me, Nicole. Among its functions is in the mechanical. it is responsible for the medical mechanical part that regulates the entry and pressure of air that replace the function of the lungs. The oxygen powered by Javier Martinez, it is responsible for energizing the complete fan system through the available energy. And the GUI subsystem by me, Nicole Diaz, is the responsible for um, the GUI and is responsible for facilitating the control of the ventilator through a graphical user interface or GUI to favor its employers to be able to manage it on a monitor where ventilator parameters are read and ventilator functions are adjusted. The N-square diagram, we can see how the subsystems are related and how one affects the other. Starting with the technician or person who will be operating the fan, it is followed by the power system, the control system, and finally the mechanical system. In the variable F, we see how the technician affects the control system by pressing a button with a force to activate the system, and we can see right here the F. And that's the first variable, and the description says force provided by the technician to activate the system. The second variable is this one, is the EV, and that's the energy is transmitted to the control system that causes it to activate it or run on the control system. We can see it right here. Electrical signal from power system to control system. The other variable is the OP right here. Is variable is when oxygen energizes the mechanical system to activate it. The other one is the PV for push button on or off. The next one is S, and the HC is for hertz, the signal. Is received order of the parameter program in the GUI. And the last one is WS, that is for the warning signal due to the change in parameters. It's a signal too, so it's HC for the hertz. And now we'll be continuing with my partner.
The budget. The cost of our innovation, the green power mechanical ventilator, is 3,580 per unit. An investment of 101 power mechanical ventilators requires a budget of $180,811. The sale for the 101 green power mechanical ventilators at 3,580 is 361,622 with 42 cents. The budget allocation for the green power mechanical ventilator is the mechanical system will have 81,365 with 4 cents. The control system will have 63,283 with 92 cents. The power system will have 36,000 with 162 with 24 cents. Now, I leave you with my partner Darlene to continue the presentation.
The mechanical system MOPs. Systems shall have an auto-adjusting to load capacity. Systems should have an adjustable peak pressure range of 10 to 45 centimeters cubic H2O. Systems should have an oxygen delivery of 80% when supplied with 100% O2. Systems should have a dead space of 4 plus minus 3 ml. System will complete with 21 CFR 868.5895, 20 CFR A68.5730, 20 CFR A68.5440, 20 CFR A68.5340, FDA regulation. System should have an inspiratory resistance of 3 plus minor 1 centimeters H2O per second. System should have an expiratory resistance of 3 plus minor 1 centimeters H2O per second. System weight should be 170 grams. System should have an external dimensions of 9.5 inches per 4 inches per 3 inches. System should work with person of body mass 10 kilograms and above. The mechanical subsystem list of risks are: number one, no calibrate manometer. Mitigate by always check the calibration labels. Number two, material degradation. Mitigate by have response materials. Number three, oxygen flows does not appear. Mitigate by check quality maintenance. Number four, factor of material. Mitigate by use the response ventilator. And number five is monitor do not work. Mitigate by use the correct monitor for the system. We can see in the right Sophia risk diagram, and it explains the lower we go, the result has more likelihood of happening, and if we move to the right, has more consequence. Now I leave you with my partner Javes.
The power subsystem MOPs. System should work with available energy. System must work with gas-powered oxygen. System should have a lifespan of 15 to 20 years. System should use rechargeable batteries to power the control system. System should reduce use of electrical energy, therefore, it will reduce the cost of energy of the hospital or place that is. System should work where electrical power is unavailable. System must meet the FDA H68.2700 regulation for pressure regulator devices. System must meet OSHA 1910.253A3 regulations, which states that only approved apparatus such pressure reducing valve can be used. Here we have the power subsystem assessment with the different lists of risk and the mitigation strategies. For the risk leak in a circuit, the mitigation strategy is look for pressure leak at the gas connections. For the risk of valve malfunction, we have the mitigation strategy of replace a valve for a new one. For the out of gas, we got the mitigation strategy to change and connect other gas source. For high supply flow, we got the mitigation strategy to reduce supply gas flow. For battery failure, we have the mitigation strategy of do not overcharge the batteries. Here at the right, we have the Sophia risk diagram with the likelihoods and the consequence of the leaks of the list of risk. Now, we're gonna continue with my partner Nicole Diaz to continue the presentation.
So now the control subsystem. The MOPs for the control subsystem, the system should give an alert for any irregularity with the patient. The system should give an alert for any irregularity with the ventilator system too. And the system must have a GUI that is intuitive enough to be operated by personnel with little knowledge of programming languages. The system should manipulate pressure, volume, and flow. The system should be capable of controlling the mechanical subsystem, should be have a fast reaction time. The control subsystem assessment in the control subsystem list of risk, we have the circuit interrupt signal. And the mitigation strategy is to protect the circuit with a hard case. And that's located right here in the orange. The second one is the short circuit. And we can, with the mitigation strategy, it's employing fuses and circuit breakers. And it's located right here. Then the third one is the last one is limited signals of inputs and outputs. Use controls with multiple input signals, and it's located right here in the green square. And this is my preliminary project planning. And that will be all. Thank you for your attention.